So computational complexity is the problem of actually finding the hardness of problems. And from the perspective of a pure theoretician who studies complexity theory, the stuff that we've been doing so far, talking about devising algorithms and improving their running times, that's just part of the story. That's just upper bound determination. There's a whole other set of work that has to go into finding lower bounds on the hardness of problems. And that requires very different techniques from the kinds that we've been talking about up to this point. So it's worth pointing out that what theoreticians often really like to do is if they find an upper bound for the hardness of a problem and they can find a lower bound that matches it, then you know exactly the complexity of the problem. It has to lie between those and they match, so therefore it's exactly that. So as I said, we're not going to get very involved in proving lower bounds for different problems, but this argument is actually not too hard and it'll give you a little flavor for how this can be done in some cases. Imagine that we're trying to compute the max of a list of length n. Now we know an upper bound on this problem is big theta n because we can just loop through all the elements in the list and find the maximum. But how do we argue about a lower bound for this problem? Well, one argument might be, constant time is a lower bound on this problem because at the very least you have to give the answer. It takes at least constant time to do that. It's possible you can even do that well. If you're trying to compute the max of a list and you guess the number, it may very well be the max. So that gives us a lower bound. Here's another one. Big theta of n might be a lower bound. Why? Because you have to at least look at all the n items. Otherwise, there could be one item in the list that is the max that you didn't look at, and so you can't possibly return the right answer. All right, another argument might be something like this. We have a lower bound of log n for the problem because it's, finding the max is sort of like finding the winner of a tournament. You have to compare values against other values, and we might be able to actually eliminate half each time. And if we could do that, then the number of rounds that it would take before we have a winner in a tournament of n individuals, in a single elimination tournament, it's log n. So which of these do you think is the best argument in terms of a lower bound for finding the max?